Today we're going to do the spread. There's only two things you need to know to do statistics. What's the average and how good is the average? This range, the standard deviation, is the part where you get how good is the average. Can you believe it? We have the range, and this is literally the distance from the smallest to the largest. And it is useful only when you have no other information whatsoever. So that's the only time the range is important. Otherwise, everything is standard deviation. Right? And this is a really stupid name because what is a standard deviate? Right? What it really means is deviation that is standardized. And that means it's deviation adjusted for the mean. The letter, or what stands for standard deviation, is, for a sample, a little letter S, and for a population, it's a sigma, which is a Greek little letter S. And the calculation, we're going to go through the calculation, but you don't have to calculate it anymore. You get a list of numbers, you punch a button, and bang, up it comes. So the important thing is, what is it doing? How does it get there? What do you do with this? All right, start up Excel. Come on, where'd you go? Get in Excel. We need a page. And I'm going to put in the numbers 3. And it doesn't matter where you are. You just need a list of numbers. 3, 5, 7, 8, 13, and 15. 3, 5, 7, 8, 13, and 15. We have 6 numbers. Our sample size is 6. And we're going to calculate the standard deviation. Right. First, we need the average. And you can go to the bottom of the list, and you can do equals average and then mark those numbers, or you can go to the automatic commands up on the top there, and one of them is average. So I'll just click on average, and it does what it thinks I want to do. Press enter, and there's the average. All right, what I need to look at is how far these numbers are from the average. And that's going to give us the standard deviation. So next to the 3, we want to subtract the average from the 3. So we need equals whatever is in that spot right there. I've got mine in F29. Minus, and then I'm going to click on the cell with the average. I'm going to copy this down, so I need to lock the cell reference to the average. So go in your formula, and in front of the letter for the column, put a $sign. Then move over in front of the number for the row and put a $sign. And now I've got whatever's in this cell minus whatever's in that cell. And when I copy it, it's going to do whatever's here minus that, whatever's here minus that, and so on. So enter, and the 3 is 5.5 below the average. I copy this down, And I want to be sure I don't get the average again. And here is the difference from the average of each of these numbers. All right. The 3 is 5.5 below. The 15 is 6.5 above. If you get the average of these numbers, you're going to get 0 because the average is the middle. Adding these up doesn't do us any good. What we need is the square of these numbers. So go to the side beside the 5.5 and square it. Equals, click in there, and then square is the caret above the 6 on the keyboard, and 2. But then we square those things. And I'm going to copy that cell down. So I'm going to square each of these numbers. This is the important thing. I've squared them. There is no negative number now. They're all positive. I don't have negative difference. I can only get positive difference. So I have here the square of the difference from the average. I'm going to add these up, and I'll use the sum command just because. And that's the sum of the squared differences. This is standardized. When you subtract the average from something, from your observations, you are beginning standardization. That's why it's called the standard deviation. It's deviation standardized on this data. Then take this, and we need the average squared difference. But instead of dividing by 6, we have to divide by n minus 1, which is going to be 5. So if we go below, I'm going to divide that total. I'm going to divide that by 5. And if you look on the MyOpenMath, where was it? Here, this is n minus 1. This is because this is a sample, and we have degrees of freedom. We'll get to degrees of freedom later. In the population, it's divided by the size of the population. For this, it's n minus 1. Get a box of 5 pencils. Offer him the pencils. He gets to pick any pencil he wants out of 5. I go to him. He's got 4 choices. Go to her. There's 3 choices. Here, 2 choices. When 4 of the pencils are gone, how many choices does he have? That's degrees of freedom, the choices. And 1 degree of freedom is lost because I calculated the average. This is kind of a strange thing, but it shows up. But here, I divide that by 5, n minus 1, and I get 21.5. This is actually the variance. And the variance is the square of the standard deviation. We used to have to use variance because that's how we got to standard deviation. We went through literally this calculation, and then we had to take the square root of it. So I need the square root of this number, the square root of the variance, equals SQRT. But there's the square root, close it, so that this 4.63, 4.64 is the standard deviation for that list of numbers. This is the important part. We're going to add and subtract this standard deviation from the average so that the units have to match for both the average and the standard deviation. Suppose this is feet. 3 feet, 5 feet, and so forth. The average is in feet. The standard deviation is in feet. The variance is in feet squared. And it's fairly useless. Literally, we had to have it because we had to get to the square root of that to get to the standard deviation. So you'll see things like variance. It's history. It's old news. But one thing, I'm going to knock some decimals off of this just because. One thing I can look at to see how good my estimate of the average is how big is the standard deviation compared to the average. So I divide the average into that number. And this I'm going to divide equals standard deviation divided by the average. So that here the standard deviation is about 55% of the average. Most things have a ratio of the standard deviation to the average of somewhere between 40 to 60%, just as a general rule. If something is as low as 10%, it is very much the same. If you're making ball bearings, your standard deviation divided in by the average ought to be in the fractions of a percent, because everything's got to be the same. If we did the sample of heights in this room, or shoe size, or whatever, we'd get a standard deviation relative to the average of about 40%. So this is not unexpected. And this has got a name. It's called the coefficient of variation. And it's just standard deviation divided by the average. Standard deviation is in feet. The average is in feet. I divide them, and I'm left with a percentage with no units. So I can compare across samples. I can compare across populations. This population has a high standard deviation compared to the average. All right, think of this as bounce. Here I've got a bounce of 4.64, this big. Here's my average, and my bounce goes like this. What if the average were 100 and the standard deviation were 4.64? Now, here's the average, and here's the bounce. So that, which can I trust more? An average of 100 with this bounce, or an average of 8.5 with that bounce? So that's what this is telling us. What is the relative size of the difference in the sample? And that's what the standard deviation does for us. I'm going to take these numbers and copy them just because I'm going to screw with them, and I don't want to mess anything up. And we're going to get the standard deviation the real way. At the bottom of the list, and there's no automatic command for this, we do equals, and then STD, and up pops stdev.p and stdev.s, and there's some others in there. The stdev.p uses n as a divisor. The p is for population. Right? There are people that imagine that in statistics we know something about a population. We don't know squat about populations. That's why we're doing statistics. We're estimating things about a population. So that this one is an engineer's version of standard deviation. It's got the n divisor. The stdev.s is the one we want because the divisor is n minus 1. We lose a degree of freedom. Mark those numbers, close the parenthesis, and there's the standard deviation. Right, the only reason I did this was to show you why. How much of a contribution to the bounce does the 8 make? It's almost at the average. Its squared is 0.25. It has very little weight. Here, 15 squared is 42. So that numbers far from the average have more of a contribution to the bounce, to the difference and how much you can trust the average. The 3 and the 15 have much more effect than the 7 and the 8. 7 and 8, it's like the average. You got the average, and you get another thing that's like the average. So what? This is like you're getting pizza. You got a good pizza. You've always gotten this kind of pizza. And it's always the same. You get a pizza? Yeah, okay, it's a pizza. If you got a really, really good pizza or a really, really bad pizza, then you've got something. You learned something. So that it's the extremes that drive statistics. And one of the ways that we control statistics is we control the extremes, or try to control the extremes. So that's what's going on here. So that's the standard deviation, and the coefficient of variation is called the CV. And not many people actually use this. Because of what I was doing, it was very important to me, because it told me about what effort I was going to have to do this kind of thing. If I wanted to design a sample, what was I dealing with? How much difference did I have to capture? Right. One other thing, this divisor here is as a square root. In these formulas, here's the observation minus the average squared. That means add them up, and then divide by n. Here I divide by n minus 1, but I'm taking the square root. When I design a sample, I need sample size. How many samples do I need? But the problem becomes, because it's a square root divisor, the first one is good. The second one is worth 1 over the square root of 2. If I'm doing dollars, I spend $1 to get my first sample, I get $1 worth of information. I do the second, it still cost me $1 to get the sample, but now I only get 71% or 71 cents worth of information. By the time I get to 3, I'm only getting back 1 over the square root of 3. I get to 10, I'm getting 1 over the square root of 10. When I get to 100, I still am paying $1 for a sample, but now I get 10 cents worth of information. So that the bigger the sample size, which is what I want, the less each one contributes to information about the population. I want big sample sizes because I'm going to divide by that and squash this standard deviation down, but more and more and more costs the same and gives me less and less information. This is diminishing returns. So that I want as big a sample size as I can afford and still get something out of it. Right? In fact, in statistics, 30 is a large sample size. because by the time you get to 30, actually 25, think of it that way, 1 over the square root of 25, we're down to 20 cents worth of information for every dollar I spend. So that in statistics, 25 and 30 is a large sample size. That brings us to relative position. Relative position, and this is using the average and the standard deviation. Here's an average. And this is written X bar. Sample average is called X bar. If I go up 1 standard deviation from the average, here before the average was 8.5, the standard deviation was 4.64. If I add 4.64 to the 8.5, and I subtract the standard deviation from the average, I get a bet. This is what we do. We're betting on the average using the standard deviation. I expect 68% of population elements to be within 1 standard deviation up and 1 standard deviation down. Suppose I got the height of people in this room. We calculated the average and the standard deviation. The bet is that the next person that walks in the room is within 1 standard deviation up and 1 down with 68% odds. And that's the first statistics bet we can make. If I go up 2 standard deviations and 2 standard deviations down, the bet is 95% of the population is in those limits. This is called the empirical rule. 1 standard deviation up and down covers 68% of the population. 2 standard deviations up and 2 down covers 95% of the population. How many are going to be bigger than the average plus 2 standard deviations? 95% in the middle. What's outside? Both ends. 5%. So 1 tail is 2.5%. And the other tail is 2.5%. So this is relative position. And I have another way to do this. And it's called a z-score. A z-score is equal to the observation minus the average divided by the standard deviation. So the average before, I had a z, or an observation of 3. I subtract this average and divide by the standard deviation. This is literally how many standard deviations away from the average that number is. The difference was minus 5.5. I divide that by 4.64. 1.18. Thank you. This z-score is 1.18. It means that that observation is 1.18 standard deviations from the average. everything that I bet on in statistics is based on the standard deviation and the average. And the z-score is a way to look at it, and I can compare samples. Suppose I have another sample of shoe size. I got an average and a standard deviation. I can find out how many standard deviations an observation is from the average, and I can compare this 3 and 8.5 to something entirely different based on the z-score. When you look at this, what's the z-score going to be for a number 2 standard deviations above the average? Here I've got a number x plus 2s. I'm going to subtract the average from it and divide it by the standard deviation. This becomes 2 standard deviations divided by the standard deviation, which is 2. So that this value, x bar plus 2s, has a z-score of 2. This one has a z-score of minus 2. This is a z-score of minus 1. This is a z-score of 1, and this is 0. This is standardized. That's what the z-score is. It's the standardized score. And I can go from the observation, the average, and the standard deviation to a standardized score. So now, my empirical rule says that if I standardize things, 68% are going to be between minus 1 and 1. 95% are going to be between minus 2 and plus 2. This is the main bet. I got a 2/3 chance of being in the middle here. I have a 95% chance of being within plus and minus 2 standard deviations, and I only have a 2.5% chance of being above or being below that. And that z-score tells me how many standard deviations away from the average a value is. So no matter what I do in terms of numbers, I can get a z-score. And for this equals, need n 3 minus 8.5 divided by 4.64. And there's the z-score for the 3. I copy this down. I can tell how far out each of these is. The 15 is 1.4 standard deviations above the average. The 3 is 1.18 standard deviations below the average. The 8 is basically at the average. This is the basic bet in statistics. 1 standard deviation up, 1 down, 68% bet. 2 standard deviations up, 2 standard deviations down, 95% bet. What's the bet in here? This is called the empirical rule, but this actually is as accurate as you ever need to be in statistics. If you don't remember anything else in statistics except 1 and 2, you got it made. 2 up, 2 down, 95%. 1 up, 1 down, 68%. What's the bet in here? I got 95% overall, 68% in the middle. What's the 95 minus 68? There's a 7, and what is that, 27? 27% is between here and here, and there and there. What's in that interval? And I can make any bet I want based on 1 and 2. I've got a 13.5% chance that a number is between -2 and -1 standard deviations, 68% that it's in there, 13.5% that it's there, 2.5 on either end, and those are the bets. But always remember this. Z-score is measurements in standard deviations. So everything in statistics is based on the distance from the average measured in standard deviations.